Alright, okay, so welcome everyone to part 2 of the Math2621, Math2521 revision seminar. And we're starting off with topic 3, which is series. So just give me a moment, just checking something. Alright, so to get started, we're going to be looking at complex power series. So it's a sort of continuation of the idea we've seen before with real power series. And so there's sort of expressions that look like this, like A0 plus A1 Z minus Z0 plus A2 Z minus Z0 squared, and so on and so forth. Now, the idea here is that we have some center Z0, and one really important thing that we're interested in is where does this power series converge? And the answer is inside something called the radius of convergence. So it's sort of defined by the largest R. So the power series converges inside that open ball centered at our center with radius R. Now, if it only converges at the center, then we say the radius of convergence is 0. If it converges everywhere, then we say that the radius of convergence is infinity. A really important theorem here is that a power series can be integrated and differentiated term by term inside the radius of convergence. And we'll see why that's very useful soon. So before we move on, we do need to look at how do we actually determine this radius of convergence. And the answer is we can use the ratio test. And it's a matter of just finding this limit as n goes to infinity of an over an plus 1 absolute value. And remember, an, those are our coefficients inside the power series. Alright, so let's look at an example here to see what's going on. So in this case, we have a power series that's n times z plus 3 to the power n. Alright, so first find the center and radius of convergence of the power series. So center is quite easy to find. We can see that this is the same thing as minus 3, okay? Which means that our center will be at -3. In terms of radius, remember our radius of convergence can be found using this ratio test. And then we're looking at an over an plus 1 absolute value. In this case, our an's are just n. So this is the limit as n goes to infinity of n over n plus 1, which is just 1. Okay, and so our radius of convergence is 1. Alright, next, let's find an expression for h as an elementary function. So at the moment, we've sort of written h in this power series form, but maybe we're interested in seeing if there's a simpler way to write it. Oh, okay. Looks like I have a slight problem. I'm gonna change this stream. Okay, there we go. Sorry, this is not 1081, this is 2621. Alright, so moving on. So what we want to find is an elementary expression for this h that's not like a power series. So a very simple way to write it. And this is where our differentiation / integration idea becomes useful. So at the moment, the way the power series is written, there's no way for me to like actually calculate the sum of this series, right? And so one major idea that we probably got to get used to with power series is that we kind of want to transform everything to a geometric series. And the reason why is because let's look at a simple geometric series. For example, like a plus ar squared, dot, dot, dot. So yes, yes, that's right. So this is a very simple geometric series, and we know from first year that its sum is just a on 1 minus r. So it's really easy for me to calculate, what this geometric series is inside of its radius of convergence. And so I want to transform this into some geometric sum. And so now we kind of need to look at, okay, what's the problem? Why is this not a geometric sum? And the answer is because of this n, right? It looks like z plus 3 plus 2z plus 3 squared, right? And so we need to kind of get rid of that n. Now we're going to think about our differentiation idea. So notice this looks very similar to a derivative, right? So I'm going to write it out. N z plus 3 to the power n. Looks similar to a derivative. Why? Because what is the derivative of z plus 3 to the n? We take that n down, and then we're left with this. So the only difference is that we have one extra factor of z plus 3 here. And so what we're going to do is take out that z plus 3 to the front. Okay, and now what I have here is precisely the derivative of z plus 3 to the n. Okay? And what I can do is rewrite that as z plus 3. And I can take the derivative out to the front of this power series. And the reason why is because of our theorem that said I can take the derivative out to the front. Okay? Because our power series can be differentiated term by term. Now, notice that this is precisely a geometric sum, okay? Precisely a geometric sum, because it looks like 1 plus z plus 3 plus z plus 3 squared plus ... all the way up to infinity, right? And so notice that inside of my radius of convergence, I can just say that this equals 1 on 1 minus z plus 3, using a on 1 minus r formula. Okay, so if I actually do that, I notice that that's the same thing as the derivative of this expression. Okay, and you can simplify it and it becomes the derivative of this expression. And now we can actually just calculate the derivative of negative 1 and z plus 2. It's not too bad. And what we get is this. And so this is our elementary expression for h of z. And you can see what I mean by elementary is that it just expresses some quotient function. Alright, and now the last part of the question was to find where h is quote-unquote analytic. So analytic just means where can I write h as a power series? And the answer is quite simple. It's just centered at my center with radius equal to the radius of convergence. So it's just the open ball centered at -3 with radius 1, which is my radius of convergence, right? And so that's where it can be written as a power series. Alright, so let's move on to another example now. So we have this power series now. Now find the center and radius convergence of this power series and find an expression for f as an elementary function. Alright, so the first thing we're going to note, in order to find our center, notice that all of our power series are written in this form, right? Z minus Z naught to the power n. Okay? So the issue is that my coefficient of z is not 1. So what we're going to do is take out a factor of 2. I'm going to rewrite it like this. So 2 to the n plus 1, z minus 5 on 2 to the n. So I take out that factor of 2, so it's easier for me to actually determine that the center of convergence is -5 on 2, sorry. So we rewrite it like that. It's clear to see that the center is 5 on 2. And now the radius is given by the ratio test again. And so you can see that if I plug in my coefficients, which are now 2 to the n over n plus 1, divided by 2 to the n plus 1 over n plus 2, we can actually calculate this. This part goes to 1 in the limit, this part goes to 1, and then this goes to a half. And so we're left with a half. So the radius of convergence is half. Alright, now we found the center and radius of convergence. Now we want to find expression for f as an elementary function. Okay, so to do this, we're going to note one thing, is that kind of similar to the last one, we want to rewrite it ideally as some kind of geometric sum. Now the issue is not, instead of the last one being n, now it's 1 on n plus 1. So we want to somehow cancel out 1 on n plus 1. And to do that, it's sort of a matter of taking derivatives again. So what we kind of do, instead of, in the previous example, I wrote this as a derivative. because that allowed us to bring the n down. right? But now what I want to do is cancel out this 1 on n plus 1. So what I'm going to do is take a derivative of the entire function itself, okay? So what I mean is, if I take a derivative of the entire function, then I can bring that n down. But the issue is that it doesn't quite cancel out, because what we really need is a z minus 512 to the power n plus 1, because that would allow me to effectively cancel out that n plus 1. Okay, so in order to do that, what we're going to do is a few steps. The first one is to multiply everything by z minus 512. So the reason why we do that is because this now makes it a power n plus 1. Okay, and now what we want to do is cancel out this n plus 1. And to do that, we take derivative of everything. The reason why is because then I can take that derivative inside the sum, and then notice that inside here, I can actually just calculate that derivative. It's not too bad. You can see that the n plus 1 cancels out really nicely, and we're left with just this. So essentially, we're left with this expression. So you kind of want to practice a few of these questions to get an intuition for what steps you kind of need to do, but they always involve some sort of multiplication or differentiation inside the sum, and that allows us to simplify it and make it into a geometric sum. And the reason why this is really clearly a geometric series, because if I rewrite it like this, you can see that it's just 2z minus 5 to the power n. Yes. So we're gonna convert to standard form, and so we see that, what I mean by convert to standard form is we want to start it from n equals 0, right? So notice that this thing here is the same thing as n equals 0, infinity, z minus 5 to the n. Okay, so we kind of got to get used to that, swapping the indices. And the reason why we want it to be standard form is because you can immediately say that I can immediately say that using the geometric series, this is just 1 on 1 minus 2z minus 5, which is 1 on 6 minus 2z, right? And then we multiply here, and then we get this. And then we can rewrite it in this form using a bit of algebra. All right, now, we haven't quite finished the question, of course, because there's still a problem of we haven't actually found z yet, f of z. And if we look at our right-hand side, notice that we have this. Okay, so we clearly have to take an integral with respect to z to sort of cancel out that derivative. And if we integrate this, it's clear to see that this just integrates to a log. So we get minus z minus half log of 6 minus 2z plus c. All right, now, obviously we need to find our constant now, so we're going to have to use some of the properties of f that we know. So firstly to look at this function, where's the singularity? Where's the singularity? And the answer is clearly when z equals, when the inside of this log equals 0, okay? And so we kind of avoid that point. What we want to do is sub in a point that makes this really easy to simplify. And looking at this, the point that makes it really easy to simplify is clearly just eliminating my left-hand side by setting z equals 512. So we're going to set z equals 512, okay? And that allows me to sub this in. Now notice that if I sub 512 here, I get 1, and log of 1 is 0. And so I really just have 0 equals negative 512 plus c, so c equals 512. So that was nice to calculate, because we kind of just canceled out really easily. And so from here, we kind of sub in, we get this expression here. Now there's one major issue, is that if I kind of divide across to get f of z, I'll get this, log 0, 2z minus 5. But the issue is that we kind of have, this issue. What happens when z equals 512? And now you might say, oh, it's just undefined at that point. But that's where we have to return back to what we were actually doing in the first place. What we were actually doing was finding an elementary or expression for f of z written here. And now, if you notice this, it actually is well defined at the point 512, right? Because it's inside our radius of convergence. So it's very well defined. And so to actually determine what it is, we can just sub it into here. And we notice that if we sub 512 in, we just get 0. So while, written in this form, like when it's written in this form, it's not clear what the value is, because, you'd say it's undefined. But if we go back to our power series, we can see it is actually well defined, and it's just equal to 0. Alright, so we're going to move on now. So we're going to move on to Taylor series. So we've seen Taylor series before when it came to, first year calculus, right? But now what we're going to be looking at is Taylor series for complex functions. So if a function is holomorphic, in some region, then its Taylor series is very well defined. And nothing changes from the real number case to the complex number case. Essentially, the formula looks the same. So we'll do an example of calculating a Taylor series. So determine the Taylor series of this function, z plus 2 e to the 3z. Now to do this, the easiest way to do it actually is just to realize that e to the 3z has a very straightforward Taylor series. Okay, we're very comfortable with the Taylor series for e to the 3z, right? In fact, it will just be this expression here. So this is my expression for the Taylor series for e to the 3z. So you should be kind of very familiar with exponential Taylor series, as well as sine and cos, for example. All right, now what we do is to find the Taylor series of the whole thing, we can expand it out. So if we expand it out, we'll get this. We'll get, here we'll have, we sort of multiply that z in, we'll have 3 to the k, z to the k plus 1 over k factorial. And then we'll have 2 times the original Taylor series. So 3 to the k, z to the k over k factorial. Now what we want to do is combine this back into one whole Taylor series. And the issue is that the way it's written here, I have a z to the k plus 1, but I have a z to the k here. And so what we do to cancel that out is to kind of shift this forward by 1. And that allows me to rewrite it as z to the k here like this. Okay, so a bit confusing, but essentially if we shift it forward by 1, I now have a power of z to the k, so I can sort of combine these series together. Although the only issue remaining is that this is k equals 0 here. So we just pull out the 0th term of the series, which is 2, and then we can combine them together inside the sum and we get this. So the coefficient looks a bit terrible, but that's sort of the best we can do. Alright, so now Taylor series are fairly well behaved, but now we're going to look at something called a Lorentz series. So Taylor series were for the case where our function is well defined and holomorphic. Now for Lorentz series, there are points where a function may not be holomorphic, right? But we can still represent the function using a power series. We just can't use the Taylor series, so we use obviously a Lorentz series. Now what actually is it? Well, one way of thinking about it is, let's say I had some function, right? And this is my complex plane. And so let's say I have some point called z0. It's some singularity, and there's also a bunch of other singularities. Let's say all of these little dots are singularities. Now there's some point z, and I want to calculate, what is f of z as a power series. And it's clearly not, it's not a singularity. The function should be well behaved here. But the issue is that there's a whole bunch of singularities, and I also want to calculate it, with respect to my z0. So how do we actually think about it? Well, we can't just take this giant, circle here, because the issue is that we're including a bunch of these singularities, right? And so to kind of exclude the singularities, we consider an annulus. So you can see that if I choose this giant annulus here, centered at z0, then I include the points z but I exclude all of my singularities. And so I'll still have a very nice power series at the point Z, and I can, avoid worrying about all of these singularities. So, what does the actual power series look like? Well, sorry, something's going on. Oops. My phone, sorry. So what I was saying was that what is the actual expression for the Lorentz series? Now, essentially, again, we're going to be looking at that annulus. So take all of these singularities, exclude them out, and the function should be holomorphic on this annulus. And now, in order to account for that, instead of just having positive powers, we now have negative powers. So an example of Lorentz series could be, 1 on z squared plus 1 on z plus 1 plus z squared. That's an example of Lorentz series. So we now include negative powers. And so this is our Lorentz series. So let's do an example. If it doesn't really make too much sense, we'll go through an example. How do we actually determine a Lorentz series? So first thing to note is, the first question should be, where, what is my center of the Lorentz series? And then you tell us to calculate it in this annulus, z minus 1 greater than 1. So it's always a good strat to sort of draw this out a bit. So that's our point 1, and our region that we're looking at is this red area. So outside, excluding that circle. So it's centered at 1, and it's z minus 1 greater than 1. Okay? And you can see that this works very well, because where are the non-holomorphic points, so the singularities? They're at 0. 0 is excluded, and they're also at 2 and 1. So all of those singularities are excluded. So this annulus works, right? So now to calculate it, remember our Lorentz series will be expression of the form, including negative powers up to positive powers of Cn, some coefficient, times, now in this case, it will be of the form z minus 1. Okay? Remember, that's because our center is at 1. Okay? So, to do that, we first split it up into partial fractions, because we don't really want everything multiplied together. And now, what we'll notice is that I already have this term. Notice that that's already a power of z minus 1. It's z minus 1 to the negative 1. Okay? And so that's actually constitutes part of my Lorentz series, right? Because it was of this form. So that constitutes part of my Lorentz series. Now the issue is this 1 on z and 1 on z minus 2. And so what we'll have to do is actually write them in terms of powers of z minus 1. And so naively, the best thing that we can do is sort of say, okay, we have 1 on z. Now I want that to be in terms of z minus 1. So I could just do z minus 1 plus 1. And now the question is, how do I actually, determine this in terms of powers? We can use a geometric series, because I could rewrite it like this. Agree? And that's actually a geometric series. In particular, it's this geometric series. Right? So on and so forth, right? Now the question is, does this work? And the answer is no. And the reason why is because, does this converge? The answer should be no, right? Because, sorry, what is the condition for convergence? We need that z minus 1 modulus to be less than 1. Now we can ask ourselves, is that the case? And the answer is definitely not, because we're looking at, what region are we looking at? We're looking at outside of this, where z minus 1 modulus is greater than 1. We're looking at this region in this red area. Okay? So this doesn't converge. This won't work. However, we can do this trick. Okay, we can do this trick, and that involves taking my expression here, and previously I used this as my 1. What if I use this as my 1? And what I mean by that is, what if I divide everything by z minus 1? Then I get this, right? And now notice that this thing, or first of all, let me rewrite it to be like this. So it'll be like this. In brackets, 1 on 1 minus 1 on 1 minus z. And notice that this thing here will converge, will definitely converge, right? Because I know for a fact that modulus z minus 1 is greater than 1, which means modulus 1 on z minus 1 is less than 1. So this converges. Now, in particular, it will converge very nicely to this geometric sum. Okay? And now we can do the same thing with this z like minus 2 term. So I'll quickly illustrate that. Let's add a page. So if we're looking at the 1 on z minus 2, remember we want to write that in terms of z minus 1, so we'll do it like that. Okay? But again, the issue is that, if you think about it, this thing won't converge, so we have to do that division trick. So we have to make this our 1. Okay, so we'll have 1 minus 1 on z minus 1. And so that becomes 1 on z minus 1 outside of 1 on 1 minus z minus 1. And remember that this thing will definitely converge because we have the fact that this is greater than 1, so this is less than 1. And so this converges to the geometric sum n equals 0, infinity, sorry, a bit messy, in fact, this will be very nice, so it'll just be 1 on z minus 1 to the power n. Right, so we get this. And now, in order to determine the Lorentz series, look, we're very, very, very close to my Lorentz series. And what we're going to notice is that we can kind of combine this a bit. So I'll combine it to say this is going to be, let's see, 1 on, so infinity, 1/2 negative 1 on n over z minus 1 to the n plus 1 plus 1/2 1 on z minus 1 to the n plus 1. Okay, and so we can kind of combine this together to say that's 1/2, sorry, I'll rewrite this, 1/2 negative 1 to the n plus 1, 1 on z minus 1 to the n plus 1. Okay, and this is my Lorentz series just for getting this term. So notice that what I'm trying to say here is that to actually write this out, we want to say, okay, it's like a Lorentz series like this, and then we just specify what the coefficients will be, and the coefficients are just going to be, you can just read off what this is, right? And also don't forget to include that term, and then we should get this as our Lorentz series. Okay, so we can say this is our Lorentz series and these are the coefficients based on my calculations. All right, so we'll move on to another example. And so find the Lorentz series for f in powers of z minus 2. Okay, one sec. Okay, so to do this, right, what we're going to need to do is draw a little diagram, because the question is, what is our annulus? We were given the annulus earlier, but now we don't know what our annulus is, so we're going to have to figure it out. Now, where are the singularities? Well, the singularities are, we can just read this off. Immediately, one singularity is at the point negative 2i. We also have a singularity at 4. And our function is well defined at 2. And we also want to find it so that it converges at the point I. Okay, that was a lot. But essentially, we know the function has singularities here and here. And we're centered at here. And what we want to do is actually calculate it here. So what that means, to actually calculate it here, I needs to be inside our annulus, and all of the singularities need to be outside of our annulus. Okay? And so in order to do that, what we can do is consider our center and the distances between all of these points, and then sort of order them. So first of all, this distance here is 2. This first distance is 2. We'll call that 2. This distance here will be 2 root 2, right? And this distance here will be root 5. Should be right, yes. And now notice that what we have is clearly 2 is less than root 5, which is less than 2 root 2. And so what that means is my annulus will look like this. I want to first do this inner annulus here and make this my outer annulus. The reason why is because notice that this first distance here is 2, which is the smallest, which means I exclude this first red point. And then now this distance, root 5, is inside of our annulus, so I can calculate it. And this is the largest distance, so I'm making sure that this is the outer edge of the annulus, and so that this point, negative 2i, is excluded. So what we're going to say is that our z minus 2, so the distance from the point 2, must be less than 2 root 2, but also greater than 2. Okay? And so this will converge at I and exclude all of our bad singularities. Okay? Yes. So there we go. And so that's our annulus that we're looking at. So now let's actually calculate it. So we want to calculate it in terms of powers of z minus 2. So we'll first look at this expression. This is f of z equals, what is it, 2 on z plus 2i plus, so minus 5 on z minus 4. Okay, so remember the same thing that we wanted to do, kind of express it in terms of a geometric series, right? So to express it in terms of a geometric series, it's going to look a bit like this. And remember, it needs to be in terms of z minus 2, right? So we need a z minus 2, and we need to add plus 2 plus 2i. And then here will be 5, and it'll be z minus 2 minus 2, right? And now to continue, now we need to think about our convergence. So in other words, do we need to divide in this case? And so we'll look at this first one. So we have a z minus 2 and 2 plus 2i. We note that z minus 2 is less than the modulus of 2 plus 2i, which equals root 8, right? Which means that z minus 2 on 2 plus 2i has modulus less than 1. And so that actually works. We just need to divide everything by 2 plus 2i. So we'll write it like this. Right? Does that make sense? And then that works perfectly fine because of our annulus. Now let's look at the other one. Look at z minus 2 on 2. So we're going to note that z minus 2 is greater than modulus of 2 based on our annulus, right? Which means that we will need to divide by z minus 2 in order for this to converge, because z minus 2 on 2 is greater than 1. So we're going to have to write it like 5 on z minus 2, 1 on 1 minus 2 z minus 2. Okay. And now notice that these will become nice geometric sums. This will become this geometric sum here, and this will become this geometric sum here. Okay, and now we just need to simplify a little bit, and so we can write it like this. And so to write our Lorentz series expression, we kind of just see, okay, we have two different expressions here. But first notice that this corresponds to the negative powers. In fact, this corresponds to powers, which powers actually? -1, -2, -3, right? So on and so forth. Because you can see if I plug k equals 0, I get, power -1, and then we'll keep adding up. And this corresponds to powers 0, 1, 2, 3 onwards, right? So our Lorentz series looks like this. We can say that Cn will equal 2 on 2 plus 2i to the k plus 1 times -1 to the k for when k is greater than or equal to 0. Right? Because remember that this series dominates for, well, gives the only terms for like 0, 1, 2, 3. Okay? And then for k less than 0, we just look at the coefficient of z minus 2 on this. And that should be our other one, which should be this here. Alright, so now we're going to move on to actually classifying singularities. So an isolated singularity first is a point z0 for which f is holomorphic if we just exclude that point. So if I have some point z0, if I just say, look at the punctured ball around that point to kind of exclude it, then the function is holomorphic here. But it's not holomorphic at the point itself. That's an isolated singularity. Okay? So now, let's classify isolated singularities. So we can actually do that based on our Lorentz coefficients. So there are three cases, right? So the first one is a removable singularity. So there are no integers n less than 0 for which Cn is non-zero. We say that f has a removable singularity at z0. So that's to say there are no negative powers. So this basically means there are no negative powers. So there's no such thing as z to the -2. All of our powers are positive. And now let's think about what a removable singularity is. Well, based on kind of what we know from real analysis, there are some functions, like for example, I'll give you an example. Looks like this, like a function like this that has like a hole. You'd say that this function is not continuous, but we could redefine it as a piecewise function to sort of put that back there, in which case we can now sort of remove that singularity. So these are removable. Okay, now we're going to look at poles. So some non-zero finite number of integers have Cn non-zero. So what that essentially means is, let's look at a function like this, like a Lorentz series like this, okay? And so there's nothing to the left of -5. What that means is -5 is the most negative power for this Lorentz series. And that what that means is, what we can say is that this is a pole of order 5. Okay? So that's to say that's the largest negative power that corresponds to the order of our pole. And now there's the case where we have, what happens if we have infinitely many negative powers? We can keep going on and on to the left. Then we can't really do anything to get rid of this singularity, so we call it an essential singularity. It's like you can kind of think about it as like a pole with infinity order. Okay, so we can actually use limits to calculate these, like determine what type of singularities we have. So the first one is, if the limit exists at that point, then we have removable singularity. And that sort of runs back up to this example. You can see that for this function, oops, deleted it. Clearly the limit exists at that point and goes towards that hole. And so we can kind of remove it. So that kind of makes sense. So what this means, so our second one is that if the limit does exist, but we have to multiply by this, power out the front, then we have a pole of order n. So how that works is, let's say we had a z to the -5 case. If I multiplied this by z, then I'm going to get z to the -4 So the limit won't exist still. Limit doesn't exist. If I multiply by squared, I get this. Limit doesn't exist still because we still have negative powers. But if I multiply it by 5, then I'll get this. Which means the limit does exist. And furthermore, that power that we had to multiply for the limit to first exist corresponds to the order of our pole, which in that example was 5. And then the last one is that if it doesn't exist for any k, then we have an essential singularity. Again, you can think about that as like if the powers run infinitely negative, then we can't multiply by anything to have positive powers, to have entirely positive powers. Alright, so we'll move on to poles and zeros. So we've kind of already seen this pole of order m. They say negative m here, but it's kind of just how they define it, because they say m is less than 0. Now, a simple pole is of order 1. Now, zeros, we've kind of seen this already before. A 0 is like the smallest positive power. Like the pole, remember, is the... We kind of think of think of a pole as the largest negative power, but a 0 is the smallest positive power. Okay? So in this case, this actually corresponds to a 0 of order 3. We can kind of think about it as just the multiplicity that we've definitely seen before. We can say that 0 is a root for this polynomial of order 3 because we can factorize it 3 times out to the front. Alright, so now let's classify the singularities of this function, z e to the z on z squared plus pi squared. So to first do that, we're going to have to figure out what the singularities are, and that's sort of where the function is undefined. So to do that, we can do a simple factorization. We can factorize it like this. And now we know that we need to look at the points plus minus I pi. And so we can look at them individually. So we'll first look at z equals I pi. I pi. Remember, to do that, we could do this little trick where we, not trick, but rule where we sort of look at these limits. So the first thing to note is that definitely lim as z approaches I pi of f of z won't give us anything. It doesn't exist, right? So what we'll do is multiply by my first power. If I do that, then that becomes the limit as z approaches I pi of, remember this function equaled z e to the z on z minus I pi, z plus I pi. And so this becomes z e to the z over z plus I pi. And notice that this limit does exist, because this function is well behaved at the point I pi. And so because I only have to look at the first power, that means we have a pole of order 1, in other words, a simple pole. Alright, now we'll look at the second point, which is negative I pi, and we get the same thing. We have a simple pole because we only have to look at the first power. Alright, so that's how we classify singularities. Now let's look at a very important idea, and that's the idea of a residue. So, suppose that a function is holomorphic in a punctured ball around z0 with radius r. And we're looking at the Lorentz series centered at z0. So, we can say that, because it's this isolated singularity, we'll still have a Lorentz series. And then we can write its Lorentz series like this. Now, the residue, it's called the residue of f at the point z0, is the coefficient of -1 in my Lorentz series. So for example, if this Lorentz series equaled like -5e on z minus 1 plus z minus 1 or something, right? Like etc. Notice that the coefficient of -1 will be -5e. So the residue equals -5e. Alright, so how do we calculate residues? Now, there's a nice residue formula, but this comes from our understanding of the Lorentz series. So essentially, right, we think about it like this. If you look at our Lorentz series, we have some like expression. I'll just write out this is c negative 1 on z minus z naught, c negative 2 on z minus z naught squared, c negative 3 on z minus z naught cubed, and then there's c naught and plus c1 z minus z naught, right? So this is kind of what our Lorentz series looks like when I expand it out. Now what we want to do is kind of isolate this c negative 1. So to do that, we can do this little trick. So let's say it has a pole of order n. So pole of order n, then what we need to do is kind of get rid of that pole, if that makes sense. So this will kind of cancel out our pole. Remember, if I had a pole of order n, that meant I had some power negative n. And if I multiply by z to the n, then I restore positive powers, if that makes sense. So now I can calculate limits. And then, but what we want is for this c minus 1 term. So that's why we have to differentiate n minus 1 times, because that will give us my c minus 1. And then, because we've differentiated n minus 1 times to like restore back the actual coefficient. Remember, like by differentiating, we keep bringing powers down. So we need to multiply by this to kind of cancel out the fact that we brought all of those powers down. And so what we have is, this is our residue formula. So we've got to know this very well. So let's look at an example now. So from the previous example, gz, z minus pi squared has singularities at z equals k pi. Calculate the residues at these singularities. Alright, so what we need to do is, well, calculate residues. And remember, residues were our c negative 1 term. Alright, so to do this, we first know that our singularities are at k pi, right? And as a result, we're looking at all of the residues at k pi. Now, there's a few easy examples. Okay, the first examples, before we actually calculate these residues, it's very important for us to determine what type of singularities they are. Okay, so what I mean is, in order to use this formula, we have to know what kind of residues they are, right? What kind of singularities. What that means is, what are they, pole of order 1, 2, 3, 4, right? Because that allows us to actually use this formula. So we want to classify singularity. Now the first thing to note is that all of the singularities are at k pi, but notice that we don't just have a sine term. We also have this term on the top. Okay, we also have this term on the top, which means z equals 0 and z equals pi are kind of special, that they're different from all the other terms because they are also at the top. So we'll first classify z equals 0, z equals pi. And we'll actually do z equals pi first. Now, this is actually going to be a removable singularity. And the reason why it's a removable singularity is because if you think about it like this, if we look at the point, look at z equals pi, what we have is, limit as z approaches pi of z minus pi squared on sine squared z. And that approaches z with 0 over 0, right? And when we have that 0 over 0, we kind of cancel out this power on the bottom and the top. So we can kind of think about this as, well, the limit should approach the point itself, right? And so what we'll get is just z out, so that approaches 1. And so what that means is it's a removable singularity because the limit at the point exists, right? And so If it's a removable singularity, then the residue is 0. Okay? And that's because our coefficient of C minus 1 should be 0. Alright, so z equal pi was fine. Now let's look at z equals 0. Now it doesn't quite work because the power of z and sine squared z are different. So we kind of actually expect a simple pole. And the reason why is because we kind of, from the top we approach 0, from the bottom we approach 0 times 0. So very roughly we can kind of think about it as being a pole. It kind of corresponds to like a -1 power on the bottom. And so that gives us a simple pole. Of course we need to like quickly look at that. But essentially, how can we actually prove that? Well, it's quite simple. Remember, to show that it's a simple pole, we just look at the limit as z approaches pi of z approaches 0 of z minus 0, and then z minus pi squared with sine squared z, and this becomes z squared z minus pi squared on sine squared z. And this part, remember, by the same idea, kind of goes to 0 over 0, so the limit does exist. So if the limit exists, then that means we have a pole of order 1. Okay, and so to find its residue, remember, we can just use this formula here. And to use this formula, we simply look at the limit as z approaches 0 of z g of z. Okay, z g of z, and the reason why that is because if we actually sub 1 in, that becomes 1. That means we don't take any derivatives. That's just z f z. Okay, makes sense? So it will just be the limit of z g of z in this case. And so if we calculate that limit, we'll get pi squared. And now notice that every other singularity will be a pole of order 2, because we have that sine squared on the bottom. And so we can try calculate the limit, but it does not work out nicely at all. It's very hard for us to calculate this limit because k is sort of very general. So instead, we'll have to go back to elementary methods. And remember, the residue is c negative 1. So if we could kind of find the coefficient of z minus k pi in the Lorentz series expansion of g of z, then we can find the residue, because that's the same thing, right? The residue equals that coefficient. To do that, it's kind of a difficult problem. It's actually a very difficult problem to find the Lorentz series. However, the question is not to find the Lorentz series, so we need to be careful of that. The question is not find the Lorentz series. The question is find the residue. So all we need to look at is the coefficient of z minus k pi to the -1. That's all we need. And to do that, we'll do a few tricks. So remember, our function is this: z minus pi squared on sine squared z. Alright, so now what we're going to do is find the Taylor series for sine squared z around z equals k pi. Now, that Taylor series, well, we can use this. Inside here is the Taylor series for sine z at z equals k pi, right? And then we square it to get the sine squared. So this is fairly straightforward so far. This is our we're very used to these. So it should be I. Very used to finding these sine Taylor series. Alright, so it gets a bit more complicated from here. The issue is that we're actually not really looking at sine squared z. We're looking at the whole function. Remember, g of z was z minus pi squared on sine squared z. We need to first we need to look at 1 on sine squared z. And so if we look at this here and we then divide by 1, so 1 divided by, we'll get this. Now this is an absolutely very difficult expression to work with, right? But remember that we're not working with this expression per se. We're only looking for the coefficient of z minus k pi to the -1. Okay? Now if we look at that, we can kind of simplify a little bit, noting that this can actually be turned into a geometric series. Okay, so at the moment this is terrible, but we want it to be a geometric series because then we can look at powers. At the moment we can't quite look at powers because, well, there's just 1 divided by. It's not really clear what the powers are, but that's not to say we can't calculate those powers by just writing it in geometric series. And remember, key thing here in this entire question is that we aren't interested in finding a proper nice expression for the Lorentz series. We're only looking for the coefficient of this term, right? Oops, just removed it. We're only looking for coefficient of that term. So what we can do is notice that currently it's written in this form here, but that's okay because we can write it as a geometric series by dividing by this here. And if we divide by that, it now becomes this. Agree? And notice that the reason why it's squared here is because we took out one factor of this, but it's squared here, so that's why it's squared. And so this is a geometric series, and in particular, it should become this. Okay, now this is very terrible expression. The reason why is because what it really looks like is this. So it looks like this. It's like 5 factorial, and then to the power 1, and then we have to add the whole, infinite series again, but power 2, and then we keep going on and on to infinity. So it's like an infinite sum of infinite series. But that's okay because, again, we're not interested in the nice expression for that. We're only interested in, well, what is the coefficient of the power -1 term. And so we're kind of actually there because notice that all of this stuff has positive powers. Remember, this can range from 1, 2, 3. But notice that, if you expand it, if you thought about expanding it all out, I'll just write it out for illustration purposes. Notice that this has all positive powers, and then we square it so we'll all have positive powers, and all of that will have positive powers. In fact, one thing to note is that all of the powers are greater than or equal to 2, because the smallest power is 2, and then we keep increasing powers and squaring and so on and so forth. The smallest power will always be 2. And so that's okay because, well, notice that we have this out the front, which means if I multiply that through, the smallest power is 0, okay? So the smallest power is the constant term, and in fact the constant term will be 1 on 3 factorial. And the reason why is because, again, the smallest power will be this thing itself here. That's the smallest power in this entire series. And then we have this divided out the front. So if we think about dividing this and this, we'll get our constant term, and it will just be that coefficient, 1 on 3 factorial. Okay? So that's our constant term. The reason why I'm looking at the constant term is because, well, how do we get a power -1 involved? And a power -1 gets involved from now including the stuff on the top, okay? So first of all, we need to rewrite the top in powers of z minus k pi. So what I mean is z equals z minus k pi plus k pi. And z minus pi equals z minus k pi plus k pi plus pi, or minus pi. It's a very terrible, ugly expression again, but again, we're only looking for that one term in this whole expansion. So we just need to be very careful for that term, and the rest we don't have to be careful about. We don't really worry too much about. And so if we rewrite it like this, it becomes this, right? Putting in our full expression. Okay, so this is our full expression. Now we're looking for the power. We're looking at the power of -1. So how do we form a -1 power in this expression? Well, in order to do that, notice that, remember, all of these powers are greater than or equal to 2. So they can't actually help us form -1. But what we'll do is consider like the smallest possible term for this expansion, which is this term here. And so the question is then, how do I form a -1? So we have to selectively expand here. So just give me a moment to think. Okay, well, to do that, first notice that I may have misspoke earlier. We also include power 0 here, which means that this thing can equal 1, right? Now we're looking to form power -1. So an example of how we can form power -1 is by looking at this expression. We want to selectively expand it out, which means choosing the terms that help us form power -1 and including those terms only. So notice that because this is all power, it's either constant or like greater than or equal to 2. If I took a power 2 here, then it cancelled out there, and we would just get positive powers, right? So we have to only look at the constant term. Only look at the constant term. Okay, and so for example of how we could form power -1 is to take this, multiply by the constant there, multiply by constant there, and because we're divided by the same power with 2, then we'll get a power -1. Does that make sense? So I'll give you a smaller example of what I'm talking about. A smaller example would be like 1 plus x, 1 plus 2x. The question is, what's the coefficient of x in this expansion? And we don't have to expand the whole thing out to find coefficient of x. We can just be smart about it and realize, well, we get a coefficient of x by multiplying this x by that 7, multiplying that x by that 1. But we could also do it by taking that 1, multiplied by that 2x, and then multiplied by that 1. Or we could think about it by taking that 1, multiplied by that 7, and multiplied by that 3x. And that'll give us another x term. And the coefficient of x will be the sum of all of those coefficients. And we're doing pretty much the same idea here. We're taking this, we're going to multiply, because we already have that power, we need to multiply by a constant term. Multiply by a constant term there, and we need to multiply by the constant term there. Or what we could do is take the power of, so this actually expands out to right, blah, 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 and take this here, and then multiply by that constant term there and that constant term there. And if you actually do it all out, we should get this. And this is actually not too bad to understand. Where does this come from? There's only 2 ways we could form our constant term. Sorry, not our constant term. A term with power -1. And I just went through them. So we first look at, I'll make this extra clear. We first look at taking this and multiplying by the constant term there, which gives us a coefficient of pi k minus 1, pi squared k minus 1 squared, because it's squared there. Or we take the middle term in this expression, which itself has coefficients, 2 pi k minus 1, and multiply by that constant term there. So multiply by k pi, and we'll get 2 pi squared k minus 1. And so those are the only ways that we could form our term with -1. And then so that means our residue will be this here, which is the coefficient. Simplify it nicely like that. So that was a lot of work, but essentially the whole idea behind expanding out that Taylor series and finding the sign was to illustrate that this thing doesn't really contribute to the -1 term. Alright, so I guess we'll have a very quick break, because that was a bit of a long question. Let's quickly eat something. So the next thing we're moving on to is Cauchy's residue theorem. So this was sort of expanding upon what Marcus was talking about last like on Wednesday about the generalized integral formula, and this is the most generalized integral formula, and that is this residue theorem. So let's suppose we have some domain with a whole bunch of singularities. So z1 up to zk, let's say. Whole bunch of singularities. And then we have a contour, right? In the standard anti-clockwise direction. This other way. Right? So this is our nice contour. And we have a whole bunch of singularities. And we want to calculate the integral of, f around this contour. Oops. So we want to calculate f around this contour. And to do that, we can use Cauchy's residue theorem, which says that the integral is just 2 pi I times the sum of all the residues of these singularities. So we find the residues of all these singularities, add them together, multiply by 2 pi I, and that's the same thing as our integral. And this is used in evaluating integrals around singularities, and sort of generalize all of the integral tools that we've seen earlier in the course. So best to run through some examples. So let's look at this function, z divided by 2z to the power 4 minus 5z squared plus 2. Find all the singularities of f and classify these. So remember, to find the singularities, probably best thing to do would be to factorize the denominator. So we notice that this is kind of like a quadratic, so we can factorize it like this, and then we factorize to get our factorized denominator. And now we can see that all of these, well, we can't let them, they can't be 0 in our denominator, so they're simple poles at plus minus root 2 and plus minus 1 over root 2. And they're all simple poles because they correspond to like powers negative 1 only. Like you could verify that by actually just doing like a partial fractions expansion, but we don't need that. That's the point. Okay, so we've done that. The singularities, those are singularities, and they're all simple poles. Now find the residues of f at these singularities that lie inside the unit circle. So we're only interested in the ones that lie in the unit circle. And if we look at our unit circle, root 2 is not on our unit circle, but 1 on root 2 is. So we're only interested in these ones. So to calculate those residues, remember that these are simple poles, so they have pole of order 1. So it's 1 on 1 minus 1 factorial d, and then we look at the 0th derivative, which is just non-derivative, and then we multiply by z minus 1 over root 2 to the power 1 times f of z. Okay, and then if we look at our function, it's like, what is our function? Our function is z on root 2 z plus 1 root 2 z minus 1 z plus root 2 z minus root 2. So if you multiply by this here, you kind of cancel out that term, and so it's not very difficult to calculate the limit because you can kind of just sub in, see what you get. In this case, we'll get 1/6. And in the other case, we also get 1/6. So our two residues are 1 on 6 and 1 on 6. Now, hence find this integral. Okay, so in order to do that, well, how about we first consider, we'll first consider like an integral we can immediately calculate, which is this contour integral around the unit circle, right? Because the reason why we can immediately calculate that is, well, quite simple, because using Cauchy's residue theorem, it's just 2 pi I times the sum of the residues, so we just get 2 pi I on 3. Now we have this integral, we have to somehow relate that to the integral, which was from 0 to 2 pi of d theta on, what was it, 8 cos squared theta plus 1. Alright, so, well, in order to do this, kind of think, how can I parameterize this, like, actual contour integral? And, well, it's a simple parameterization because it's a unit circle. So we'll just use the parameterization. We'll have our curve is e to the I theta from theta is 0 to 2 pi. And that corresponds, and we just kind of sub z equals e to the I theta. And so remember to do this, we need to kind of, well, we can rewrite it in, the reason I rewrite it in this form is because notice that e to the I theta plus e to the negative I theta corresponds to 2 cos theta, right? So we have 2 times 4 cos squared theta gives us my 8 cos squared theta there. Remember, we need to multiply by this. The reason why is because, remember, our parameterization will be f of gamma theta times gamma dash of theta d theta, and gamma dash of theta is I e to the I theta, so we need to remember to put that term in. And so that cancels out, then we get I outside of 0 to 2 pi d theta on 8 cos squared theta plus 1, which is precisely the integral they asked us to find. And so, considering that they're the same value, we can say that 2 pi I on 3, because we used Cauchy's residue theorem there, equals this. So this actual integral that we're looking to find, cancel the I out, and we'll get that equals 2 pi on 3. Alright, so that's not too bad so far. We're going to look at this example of a question. Now, this one's a bit more complicated, only in the sense that we don't quite, we haven't quite got the question scaffolded for us like it was in the previous one, and we have to do a bit more open-ended thinking. And so, kind of what we did before was we took some integral, like this, and we turned it into our parameterized integral, blah, blah, blah. Now we need to go the other way around. We need to see what contour integral does this correspond to. And then when we do find that, when we find what contour integral this corresponds to, then we can just find that contour integral using Cauchy's residue theorem. So to do that, we'll notice that, in general, right, our contour integrals look like this. Right? And so we kind of want to write it in the form like this. Now, first thing to note is that we have a pi, negative pi and pi, so we have a length distance traversed of 2 pi. So we're definitely looking at a circle here, some kind of circle. So we'll use a unit circle. Say let z equal e to the I theta. So we'll consider this to be our parameterization. So suppose that this is our parameterization for theta from negative pi to pi. Now, if we look at this, cos 2, so how do we rewrite this integral in terms of z now? So one thing to remember is that we do need to include that gamma dash of theta term. But I'll explain how we can include that very soon. But let me do this first. So cos 2 theta on 5 plus 4 cos theta d theta. Well, I can rewrite that as e to the 2I theta plus e to the negative 2I theta on 2. And then that can be 5 plus 4 e to the I theta plus e to the negative I theta on 2 d theta. And so that becomes 1/2 negative pi to pi of e to the 2I theta plus e to the negative 2I theta on 5 plus 2 e to the I theta plus e to the negative I theta d theta. So we can't quite turn this into our contour integral at the moment because of the problem I was saying earlier, which is that I don't quite have my gamma dash of theta in there yet. Now, to get my gamma dash of theta, consider the fact that gamma dash theta is I e to the I theta, right? So what I can do is then say this equals 1/2 negative pi to pi, and I can just divide, multiply and divide by that term. over 5 plus 2 e to the I theta plus e to the negative I theta. Then we'll multiply by this. Right, and so this will become, in terms of z, so I now can go to my contour integral formulation. That will be gamma z squared plus z negative 2 times iz over 5 plus 2 z plus z negative 1 dz. Okay. And so, in other words, I have this. Oh, sorry, not. So this corresponds to our gamma dash of theta d theta. So it's not iz, it's 1 on iz. And so we get this expression here. And so now from here, it's a matter of rewriting it in this form. So I can rewrite it by multiplying everything by z to the power 2, and so we'll get this. And now this is a like function that I can use Cauchy's residue theorem on, right? Because I can rewrite it by factorizing. Now I can see that there are, well, first of all, we're looking at the unit circle. So question are, what singularities lie in the unit circle? And the answer is 0 and negative half, because this negative 2 lies outside the unit circle, so we don't care about it. So now we only need to find the residues at these points. Now this is a pole, this is a pole of order 2, and this is a pole of order 1. So to calculate those residues, we'll first look at the pole of order 1. So the residue of f at negative half is going to be the limit as z approaches negative half of, okay, and remember, if it's a pole of order 1, I don't have to worry about the derivative. It's just going to be z plus half, so z plus half f of z. And so that becomes limit z approaches negative half of 2z plus 1 on 2 times z to the power 4 on z squared, z 2z plus 1, z plus 2. So these cancel out, and so it's just a matter of subbing it in, and then we should get 17 on 2. Not too bad, right? Then the second one is the residue of the residue for 0. Now the residue at 0, remember, it's not quite a simple pole, it's an pole of order 2, which means we'll have to worry about this formula, so that earlier formula. So it'll be 1 on 1 factorial, the first derivative of z squared times f of z. Okay, so it's the limit, sorry, as z approaches 0. And so this becomes the limit as z approaches 0 of the derivative of z to the 4 on plus 1 on 2z 2z plus 2, so 2z plus 1, z plus 2. So, if you use quotient rule and so forth and do the limit, you should get negative 5 on 4. It's not too complicated. And so that means that my integral, this thing, equals 2 pi I times 17 on 12 plus or minus 5 on 4, based on my Cauchy residue theorem. And now don't forget that the actual integral itself, like the actual one we were looking at, I just want to point out somewhere here we took out the factor of 1 on 2i, right? So this will be like the actual integral we're looking at, which was, cos 2 theta. 5 plus 4 cos theta d theta from negative pi to pi is 1 on 2i outside of 2 pi I 17 and 12 times 4. And you'll probably want to say here by residue theorem. And so calculate that, we get pi on 6. So that concludes my part, and we'll be moving on to Jason. So just give it a moment while we transition to the last topic, which is Fourier and Laplace transforms.
Hello. Alright, we'll get started off with the last topic to cover in complex analysis. So thank you for Lockie and Marcus for completing the first two parts. And we'll end off here with Fourier and Laplace transformations. By the way, my name is Jason, and I guess I'll just be covering this last little bit. I guess to preface, firstly, I'm really bad at pronouncing stuff, so if I mispronounce stuff, I probably already have with the names. Just take that into account. I'm 100% sure I'm going to mispronounce more stuff as we go along, but just be aware, it's a maths lesson, not a English. It doesn't really matter. And I guess for this last little bit, it isn't too much. So Fourier and Laplace, we're literally just going to look at, I guess, the formulas for both of them and also the inverse and just how to apply these formulas and when to use them. So let's get started with the Fourier transforms then. For this, it is a straight up formula. So given a function here, and it is integral between infinity and negative infinity, such that it's finite and converges, then the Fourier transform, this kind of like f hat thing, is defined by this integral here. So you literally just integrate your original function, multiply e to the ix psi xi. Once again, that's where I don't know how to pronounce it properly, but psi is what I usually call it. But it's just this integral here. And the other one is just the inverse of it. So it's going the other way around. You can see that this formula is basically the exact opposite, well, very similar to the other one. The key differences is the inverse is 1 over 2 pi, and here this is ix psi, while this one had a negative up top as well. So two formulas which are very similar. You can just plug it in and find the answer. We'll look at an example of how we apply it and when we apply it. So this one here, it says find the Fourier transform for the function f of x equals to negative 4 x, all in absolute values. So let me just rewrite the formula for the Fourier transform. F hat of x, or psi, is equal to the integral from infinity to negative infinity, multiply f of x e to minus I x psi dx. Alright, so this one here is not too bad of a question. So let's plug it in to the formula and see from here. So a common thing to do is just to make sure to split up the bounds because of this absolute value. A lot of times you just do need to split up between the negative and positive parts. So if we look at the negative parts first, you'll get 4 minus I psi x dx plus the integral of 0 to x e to minus 4 minus I psi multiplied by x dx. hopefully you guys are comfortable with doing this integral. It's just simply integrating an exponential. So I'm just going to jump in and just write what, I guess, yeah, I'll just jump in and just write the final answer. So it'll be 8 over 16 plus psi squared. The whole point of this is just a pretty simple application, or like a straight up using the formula to find the Fourier transform. The next part is, I gave myself some paper, so the next part is Laplace transforms. Before we look at that, we need to find something called exponentials of type A. So essentially what it is, given a function f of t, we say it's an exponential of type A if it's less than e to the at for all values. And c can just be any real number, and a is also just any real number here as well. I guess this is kind of the definition. You see the little note there. It says, roughly speaking, if a function is exponential of type A, it just grows slower than a function of the form of e to the a plus ib z. In terms of the Laplace transform, so what we have is, suppose we have f is locally integrable function of exponential type A, then consider of h of a, which is this here. H of a is a shorthand that you'll see quite commonly. Essentially what this is just the right half of a plane from A. So imagine we have our plane like this, the real and imaginary axes, and then we have a be some value here. Remember, a is some real value. Then h of a will be this part here. That's essentially what it means. If a equals to 0, which you'll probably most commonly come across, or like you will commonly come across, it'll just be like the right half, so the positive side. I guess the transform, so going to the transform, considering this half of the plane, the Laplace transform, typically given by this little L looking shape, is the integral of f of x multiplied e to the minus zt. Once again, just another formula that we're looking at here. Let's look at a practice question then. So the question is, find the smallest real number a such that sine is of exponential type A. So essentially finding what exponential type A sine is. And then we do the Laplace transform on sine, where it is defined. So remember, where it is defined is just on h of a. So it's defined for h of a, and then we just need to find what a is first. To do this, we just simply look at, if we look at sine of t, we know this is less than or equal to 1. So the magnitude of it's less than or equal to 1. And 1 is equal to e to the 0 of t. And I guess by definition, that just means that sine of t is bounded by e to 0 t, therefore it is of type 0. So then that means it's defined on h naught. The second half of the question is just find the Laplace transform of sine t. So to do this, we just need to use a formula. So our formula was the Laplace transform of z is equal to the integral from infinity, 0 to infinity of f of t e to the minus zt dt. Alright, so let's plug in our value here. So that's integral 0 to infinity of sine t e to the minus zt dt. Next is using integration by parts, I guess. So that's minus 1 over z sine t e to minus zt from 0 to infinity. So this is here to here's by parts. Plus 1 over z integral from 0 to infinity of cosine t e to minus zt dt. Hopefully you're all fine with me not going step by step for the by parts, but hopefully everyone here is comfortable with that. And then what we get in the next step is to use by parts again to integrate this side. For the sake of simplicity, I might just skip around. Never mind. I'll go in full. So what we have here is 1 over z squared cosine t e to minus zt from 0 to infinity minus integral 0 to infinity sine t e to minus zt dt. And then what we get is this part here was what we originally had up here or up here. So this here is the Laplace transform of f. And just writing it out, that's 1 over z squared. If we make the substitutions of the bounds into here, you'll just get 1 minus the Laplace transform. Sorry, when you make the subs here, you just get 1, and this side here is the Laplace transform. Finally, we want to find the Laplace transform. We just rearrange for what we have. So that's LF of z brackets 1 plus 1 over z squared is equal to 1 over z squared. And then finally, just rearranging, you should get something along the lines of this. So I guess this is our Laplace transform, and as we said, as we found out earlier, this is defined on h0. And remember, h0 is just the right side of 0 on the plane. All right, sweet. So that's that question there. The next one is just looking at some properties of Laplace transforms. First one is the Laplace transform holomorphic. All right. So this, once again, one of those words I can't really pronounce, but essentially, well, it's analytic. It's the same thing as analytic or regular, and essentially just means differentiable at every point. I guess in where it's defined. So that's what that means. And it's defined by this here. So the derivative of the Laplace transform f is equal to the Laplace transform of g, given that g equals to minus t times f. That's the first one. Second one is if you multiply f by an exponential, and that's what g is, the Laplace transform of that is just z plus a. Next one here is when you have t over a, it becomes this here. And finally is looking at when f is differentiable, f dash will have the transform of z times Laplace of f minus f naught. So these four are just, you can kind of treat them as just four formulas and just memorize them. They're really useful when you try to find different transforms, rather than going from the definition, like of like the integral 0 infinity e to the z tf dt stuff. So rather than going straight from definition, you can do it using these four different, I guess, formulas in a sense, or properties of the Laplace transform. I guess another one is that the Laplace transform is actually linear. So if you have like L of f, well, if you have f equals to g plus h, L of f equals L of g plus L of h, like that. So it's linear in that sense. All right, let's look at this problem. It says, suppose that f, f dash, f double dash, all the way up to n minus 1 are continuous differentiable with the transform defined on h of a. Show that this formula here is true. I guess just to approach this, we'll be using induction. And I guess let's start off with the base case. So for a base case when n is equal to 0, that is pretty evident. So what you have is, that means the Laplace transform of f equals z to the power of 0 Laplace of z, like that there, which is clearly true. So this is the left-hand side. This here is the right-hand side. Now let's assume true for k. So we're assuming that this here is true. Sum from I equals to 1 to k of z to the k minus I, f of I minus 1 naught. All right. Let me just move that across so you can, jokes, you can't really see it much better. But I guess this is our assumption here. I'll just write a star so when we refer to it, we know what we're looking at. All right, now let's tackle the inductive step. So for n equals to k plus 1, we have the left-hand side, which is L of f k plus 1 of z. And then remember from one of the properties up here, we have this here. So what we can do is essentially use this and have this here. And then the next step is from assumption. We have the plus of f of k here and the plus of f of k here. So from our assumption, we can sub in the right-hand side there. Z to the k, L of f of z minus the sum from k to 1, z to the k minus I, f of I minus 1 to the 0, minus f naught. Wait, sorry, this here should be f of k. I think this formula generalizes to k. Sorry, so made that little change up here. All right, continue on. So that's z to the k plus 1, f of z minus. Now when we multiply the z into this sum here, we can simply just do it as z to k minus I plus 1, f of I minus 1 naught minus f of k naught. And then now we can just bring in this f naught into this large sum overall. So then that's just equal to and note that we just changed up here to include k plus 1 when we bring this f inside it. And yeah, that here would equal to the right hand side. I guess I didn't write it out, but hopefully it's easy to see that this here is equal to the right hand side of the expression we want to show. All right, so that's that question. Move on to the next one. So now we're looking at the inverse. So we've briefly looked at Fourier transforms, the inverse of Fourier transforms, Laplace transforms, and now we're going to look at the formula for the inverse of the Laplace transform. So once again, very similar to how the Fourier transform and the inverse of Fourier transform are quite similar. In the same sense, the inverse of the Laplace and the Laplace itself are very similar as well. So you'll notice it is also multiply this exponential thing, but rather we have the Laplace on the inside and to get the inverse. What's interesting though is that there's also this other theorem for the residue form of the inverse. So assuming that there is some positive constant m and k such that f of the Laplace of f is less than or equal to this, what we can say is that the inverse is actually equal to the sum of the residues of the Laplace transform multiplied by e to the zt. Typically, you would actually use this residue formula rather than directly computing the integral up here. A lot of the times they rig the question such that the residues are of the residues of simple poles, so it is relatively easy to find what the value will be. So what I'll say is always give the residue formula a shot before actually doing the manual integral of the inverse, just because it is typically a bit easier and it do rig the questions in that way. All right, and we'll look at the next formula, or the next theorem here is about the convolutions of f and g. So the convolution given by this little star symbol is defined to be this integral. And what's interesting about it is that the Laplace of the convolution of the functions f and g is just the Laplace multiplied by each other. And now we'll look at a practice question which puts all of this into use. So this question here, it says using the Laplace transform to solve the Volterra integral equation. All right, so this is our equation here. Couple things, I guess typically what you want to do, I guess it says to use the Laplace transform to solve it. So obviously we need to use the Laplace transform, but it's not just enough to use it. We then have to somehow invert it again, and then we solve our original function. I guess a little hint or foreshadowing, as I said earlier, it is a lot easier to invert the Laplace transform. There's two ways, right? The formula itself or the residue formula. And as I said, it is a lot easier to use the residue formula, so that's probably what we're gonna do. Also, before tackling this, I just want to point out a couple things. Firstly, we see we have two functions added together, right? What we want to do, as we said earlier, the Laplace transform is linear. So if we find L of f, it's simply the addition of the transform of this plus the transform of the other function, or that integral there. The second thing I want to note out is this integral actually looks pretty familiar. And what I mean by that is it is a convolution. So we'll probably be using the convolution formula as well. All right, so firstly, let's find the Laplace transform of t. And I guess a general commonly known thing. Firstly, let me write out this equation. So if we want to find the Laplace transform, apply it to both sides. So we're doing this transform here. And I guess, as I said, we want to look at the convolution. And we said that the Laplace transform of convolution is just the two functions multiplied together. So what we get is, if our inner function here is g, so you want the transform of t squared, and then the Laplace transform of f. Now we just want to find what this and this is. There is kind of a general, I guess, formula for it, where the Laplace transform of t k is equal to k factorial over z to the k plus 1. So I guess this here, it isn't directly stated anywhere, at least not to my knowledge, but it is a very common one which you will be doing quite a lot. Hopefully you guys have been doing quite a lot in your revision. And I guess how you actually would do this, or where you get this from, is if you remember, one of the properties was that the Laplace transform of g is equal to minus d over dt of the transform of f. And that's for when g of t is equal to t times f of t. Actually, I believe in the notes that we have here, we did it like this. Same thing either way though, but what's important is if we start off with, f of t is equal to t, then we do the Laplace transform, and you should get 1 over t squared, and just using the formula, or definition actually. So that's like the full integral thing here, just do that. And then you can find g of t, and then if you let g of t is equal to like t squared, or minus t squared, either way it works, you just need to find the derivative of 1 over t squared, and so on and so forth. So you do that for t squared here for g. You can keep going for each value of k. But yeah, that's how we get that formula there. All right, so with that, what we get is the Laplace of f is of, I've been using t, so it should be z since we're transforming it from t. So Laplace of z is equal to, using the formula, 1 over z squared plus 1 over z cubed L of f of z. Alright, so now that we have this, we can rearrange to find the transform of f, which is z over z cubed minus 1. And now we can finally use one of the inversion formulas. As I said, we are eventually going to use the residue formula, but let's imagine if we don't use the residue formula and do it straight from the definition. So if we use the inversion formula from the definition, that will be f of t is equal to the limit of r to infinity, the integral of this here minus ir, the Laplace of f, so z over z cubed minus 1, multiply e to the tz dz. We can take a minute to, I guess, just appreciate that this is a ridiculous integral. Off the top of my head, if I'm trying to do it, I'm not sure where to even start. So it would be a lot easier just to use the residue formula. And the residue formula states, I think actually, okay, yeah. The residue formula is this here. So we just need to find the residue of the plus of f multiplied e to the zt. And you do the sum of all of them to give f of t. All right. Then if we do that, what we can get is we essentially want to find, let's look at what L of f of z e to the zt is equal to z e to the zt over z cubed minus 1. From this bottom part here, you can clearly see that this factorizes to z minus 1, z minus e to the 2 pi over 3i, z minus e to the minus 2 pi over 3i. And then each of the poles are pretty easy to see, so it's just the roots here. So this, and this. Another thing is that you can clearly see each of them are simple poles. So then in order to find what the residue of each of them are, we can use the PQ formula, or is it PQ dash, one of the two. The formula here, which essentially says that the residue of f of z naught, if f is defined as p over q, the residue of f of z naught is just p over q dash of z naught, if z naught is a simple pole. So we'll be using this formula here then, and what we can easily see is if we sub in f, which we found, our f would be this here. So if we sub that in, we can clearly see that top part is p, the bottom part here is q, of z equals to z naught. The top part is z e to the zt. Q dash would be 3z squared. So then overall, it's e to the zt over 3z at z naught for each of them. And now we just need to do the sum of all of them. So sum of the residues will just be, so the sum of residues would just be, let me write that out. It would be e to the t over 3 plus e to the 2 pi over 3i t over 3 e to the 2 pi over 3i plus like this here. This is like a lot of algebra to kind of simplify and eventually get there. It will probably be easier to write this stuff in terms of their real and imaginary parts. So this will be something like minus 1. So instead of writing e to the 2 pi over 3, write minus 1 over 2 plus root 3 over 2i. So simplify this, and eventually, after a lot of algebra, you should get something along the lines of, so this is f of t, by the way. So f of t would equal to e to the t over 3 minus 1 over 3 e to the minus t over 2 cosine root 3 over 2t plus root 3 over 3 e to the minus t over 2 sine root 3 over 2 times t. And you should get something like that for this question. if you do have issues going through the algebra step by step to simplifying it, we will be posting the slides online, so you can follow that to get a better idea of if you made an algebra step along the way. But apart from that, that does bring us to the end of the revision. So I guess thank you guys for all coming and watching. If there's any issues that of what I have written here, once again, you can find the slides online on our website at MathSoc. Not only that, we'll also be posting like a little cheat sheet, like a revision sheet with all the main formulas that you guys will be needing for the exam. So check that out once we've posted that as well. I guess once again, thank you guys for coming and good luck for all of your exams.